Chapter 9, Deflection Beams Homework Solution. Homework 9.1. For a simply supported prismatic beam, DE, with a local moment at D, M0, this local moment is M0, please step by step determine the equation of the elastic curve, the analytical equation of the elastic curve, and the maximum deflection at the slope at the two ends, left end D and the right end E. Okay, so this is our problem. We have a simply supported beam, right side on a hinge, left side D on a roller, and at the D side we apply a local moment M0. We want you to derive the equation of the elastic curve, the analytical equation, and then calculate the maximum deflection and also the slope at the two ends. Okay. So the first step, like most of our problem, we would start from statics. We would draw the FBD or free body diagram for the entire DE beam. So what we got is something here. At the D, we have a reaction force RD, and at E, we also have a reaction force of RE. And let's assume RD pointing upward, and because RD is pointing upward, let's assume RE is pointing downward. Okay, and then that's the two reaction force, and that's no reaction moment, and then of course we have M0. So consider the balance of force. Of course, the magnitude would be RD equals to RE in magnitude, and what we draw, they are opposite in direction. And then consider the balance of moment. Consider the balance of moment at the D side. We would have M0 trying to rotate this beam counterclockwise, and that is balanced by RE times L, the force times distance trying to rotate this DE beam clockwise. Okay, because we draw RD pointing upward, and naturally we also draw RE pointing downward. So this is our balance force and balance of moment. And from the balance of moment, we would have the RE equals reaction force at E equals M0 divided by the length of the beam L, and it's the same magnitude for RD. Then let's consider an arbitrary section from left end D to an arbitrary point of G. Okay, arbitrary section DG from D, and let's draw the free body diagram again. We have RD pointing upward, which is the reaction force at D. We have M0, the external applied moment, and then to balance RD at the G cross section, there must be an internal shearing force or internal shear, and we draw it downward. We call it V. And also, at this cross section, there might be internal bending moment, mx, m for moment for location x, and x is the distance from D to G. So the balance of the force would give the internal shear V would be the same magnitude as reaction force RD, and it would be from up M0 divided by L. On the other hand, the balance of moment around the D. Of course, you can also consider around G, but let's say around the D, we would have M0 trying to rotate. This is DG counterclockwise. Mx, we also draw this way. So around the D, it's also trying to rotate this section counterclockwise. So these two trying to rotate it counterclockwise, and it's balanced by V times X, because V around G, V is trying to rotate this beam clockwise, V times X. And what is V? From up, we know V is M0 divided by L times X. As a result, the internal bending moment Mx would be just M0x over L minus M0. So now we have the internal shear as well as the internal bending moment mx. And when x is 0 on the left side, it will be internal will be just a minus m0. On the other hand, when x equals 1, the mx would be 0. Okay. So this is our problem. From previous slide, we get mx, the internal bending moment at arbitrary location x from D would be m0 x divided by L, the total length, minus m0. So the elastic curve from what we learned in chapter 9, the E modulus times moment of inertia I times the second derivative of vertical displacement or deflection versus horizontal location would be equal to mx, internal bending moment. And what is mx? From here it would be m0 divided by total length L times x minus m0. Okay, so this is our ordinary second order differential equation, and of course we would integrate with respect to x. For one time we will have ei times first derivative of deflection versus horizontal location equals to this term integrate would be m0 over 2l x squared, and this m0 integrate would be minus m0 x, and don't forget the integration constant c1. This would be the slope equation or local angle equation, and we would integrate again of this equation with respect to x. Now we would have ei times y, the vertical deflection, equals to, this is x squared, now becomes x to the power of 3, and then integration 2 comes to the denominator. We would have m0 times 6 L x cube minus, okay, this term integrated will become half of m0 x squared plus c1 becomes c1x, and don't forget another integration constant of c2. Okay, so this is in theory our analytical form of the deflection curve, and we need to determine the c1 and c2 value. Okay, and now let's consider our boundary conditions. We have two boundary conditions on the left, x equals 0, y equals 0, which means on the D side, that point cannot go up and down. Similarly, at E side, x equals L, the y is also 0 because it's supported by a hinge. It cannot go up and down. So we have two boundary conditions. Let's put the first boundary condition in. X equals 0. The first term is 0, second term is 0, third term is 0. So y is 0 means the C2 value, C2 constant is 0. Then for C1, let's consider another boundary condition. When x equals L, we know y is 0, which means we put this equation x equals L, m0 over 6 L and L to the power of 3 cancel, L squared minus half m0 x becomes L squared plus C1 x becomes C1L, and C2 we set is 0. So this whole thing equals to 0. And of course C1 would be these two combined is minus 1 over 3 m0 L squared, and move to the other side C1 and cancel L. C1 would be 1 over 3 m0 L. Okay, so that gives us the two integration constants. C2 is 0, C1 is 1 over 3 m0 L. Therefore, we would have the elastic curve. We would move EI to the right side. We would have m0 over 6 EIL x cubed minus m0 over 2 EI x squared plus m0 L over 3 EI x. Okay, so this is the analytical form of our elastic curve, and we got it. So the maximum deflection occurs when mathematically occurs when the first derivative when the local slope is 0, and this is our local slope. Of course, you can take derivative from this equation, and m0 ei, you can move it to the left side again. M0 over 2l x squared minus M0 x plus 1 over 3 M0 L equals 0. Okay, and this equation, if we we cancel M0, 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 and we times 2L, we would have x squared minus 2lx plus 2 over 3 L squared. Okay, we have a quadratic, simple quadratic equation, and therefore the minimal solution, of course, one would be positive, one would be negative, and the meaningful one would be the positive one would be, if you remember from your algebra, it will be 1 minus square root of 1 over 3L, and if you plug the number in, it's roughly 0.423L. The location from the left side D would be roughly 0.423L, a little bit to the center, left to the center. Okay. And the corresponding, once we have the location of the maximum, the corresponding maximum deflection would just put this x into the deflection curve, and we would get roughly, analytically, it's 0.0642 of m0 L squared over EI. Okay, and how do you do that? Of course, for this simplification, you can put m0 in the front, and EI in the denominator. Also put that into the front, and we have 6 at the bottom, and x is L to the power of 3, and this has L here, cancelled, L square, L square, L square. So L square put in the front, and 0.423 cube minus 3 times 0.423 squared plus 2 times 0.423, and this is our end result for the maximum Y deflection. And it's a positive number, which means it is higher than the original beam location. Finally, the last step is to find the slope at both ends, D and the E end. So at D, x equals 0, this is the slope analytical equation. X equals 0, the first term is 0, second term is 0, 1 over 3 m0 L. That is our slope times EI, so the local slope dy over dx equals when x is 0, our D point would be 1 over 3 m0 L divided by EI. Okay. Then on the other side, the E end, x equals L, we still have that equation, but then the x equals L, not equals 0, and it comes up to be m0 2L L squared minus m0 L plus m1 over 3 m0 L. And if we simplify, it would be half, 1/3, you sum is 5 over 6, and then you have minus 1, which added up together, it will be minus 1 over 6 m0 L. So the local slope dy over dx would be minus 1 over 6 m0 L divided by EI, and this is our final answer. Slope at the D end, x equals 0, and at the E end, x equals L. Homework 9.2. For a simply supported prismatic beam, uh, on a hinge at E, on a roller at the D, with concentrated load, one concentrated vertical load at G. So we know the distance from D to G is A on the left, and from G to E on the right is B. The total length for the beam would be A plus B equals L. Okay, we want you to determine step by step, which means give the derivation process the elastic curve y-x. X is horizontal location, y means the vertical up and down deflection for left side from 0 to A, and the net deflection at point G where we have the concentrated load. Okay, so this is our problem. We know how it's supported. We know the left side arm A, right side arm B, and we want to know the elastic curve as well as the deflection, the Y at point G. So like before, the first step again is still to get back to statics and draw the free body diagram for the entire beam. So this is our prismatic beam with a concentrated load at G point. To draw the free body diagram, because roller hinge, we will draw the reaction force at D and the reaction force at E, and thus no reaction moment. So the balance of force would give the total force down P would be equals to what we draw RD going up plus RE going up. So this is our first equation. The second equation is consider the balance of moment. We can consider balance moment around G that would give us RD times left side A equals RE times right side B. Okay, these two equations, and you solve them, we would have the reaction force at D would be BP over the total length A plus B, and RE would be AP over the total length of A plus B. Okay, and of course RD is B times A, AB equals to RE, A times B. Okay, so we checked it seems to be right. Then we would consider an arbitrary section DC. So for arbitrary section from D to C with X, with length of X, now let's draw the free body diagram again. Again, we have RD going upward, and then at this C cross section, to balance RD, we need a internal shear V. It's a function of X location, and this force pair is trying to rotate this piece clockwise. So as a result, at the C cross section, there must be a internal bending moment of mx. Bending moment of mx. So we are considering section DC, and this x from 0 to A, so to the left of this P. So balance of force, as we said, gives the internal shear would be equal in magnitude to RD, and what is RD? From up, it's BP over A plus B, and for the internal bending moment, mx trying to rotate it counterclockwise would be equal to RD times X if we consider the moment around C. RD times X, and what is RD? It's the same BP over A plus B times X. Okay, so we know the internal shear and the internal bending moment. Now we know the internal bending moment when we make a cut between D and G, when X is from 0 all the way to A, to the left of P. So as a result, for the differential form of the deflection curve, EI times second derivative of vertical deflection with respect to horizontal X location would be equal to what we learned in chapter 9, M, internal moment at X location, and this m is bp over a plus b times x. Okay, and this is our second order ordinary differential equation. We would integrate with respect to x to get the slope. EI times slope would be bp over ab, but with the factor of 2 times x from 1 to x squared. Don't forget integration constant c1. And to get the deflection curve, we need to integrate again. This is first derivative of local slope. Integrate again, we would get the local deflection. Transverse displacement, EI times y would be equal to bp over 2, now becomes 6ab, x squared become x cubed, c1 becomes c1x, and don't forget c2, the second integration constant. Okay, and this is the section that we choose from D to C. We have on the D side reaction force. V is the internal shear, and we know it's equals to RD, and Mx is this one. And for here, for this situation, internal for this case, we also have so-called boundary conditions, and actually we have 4 boundary conditions. One is at the left side, x equals 0, at D point, y equals 0, which means the D cannot go up, cannot go down. Similarly, at the right side E, we would have x equals L or A plus B. The y is 0 because it's on a hinge connection. The E side cannot go up and down. But in this particular case, to guarantee continuity, because we have a solid beam, the local slope normally is continuous. So at a G point, we would have 2 additional boundary conditions. One is at x equals a, or at the G point, YL equals YL equals YR. YL means the left side deflection analytical equation would be equals to the right side deflection from the analytical solution. Okay, that's about whatever we do for the deflection analytical solution, the left side deflection must meet the right side deflection. The second one is about the smoothness. Because it's a solid beam, the local slope has to be continuous, has to meet. So which means at the same G location, x equals a, the theta, the local slope from left side must be equal to the theta, the slope from the right side. Okay, so because of this concentrated load, we have 2 additional boundary conditions, and these are necessary for us to solve the equation. Similarly, when we consider the right side, when x is greater than a but smaller than a plus b, okay, from G to E, x is greater than a but smaller than a plus b, so somewhere from here to here. Now we consider the balance of moment around the C. Again, of course, we can take this section CE. We have RE reaction force at E. We have internal shear Vx, and the magnitude would be the same as RE, and RE is going upward, so the Vx has to, on this part, has to go downward. And this force pair is trying to rotate the CE section counterclockwise. As a result, at the C cross section, there must be a internal bending moment mx, which is the same when you look from the other side. Mx is trying to rotate it clockwise. And then let's consider the balance moment around C. We would have mx trying to rotate it clockwise equals to RE trying to rotate it counterclockwise times the distance, this distance, which is a plus b, the total length, minus x. Okay, and what is RE? RE from previous page we know is a times p over a plus b. A over essentially total length times P. Okay, and if we expand it, AB and AB would cancel out. We would have AP at the end, and then we would have AP over A plus B times X. Don't forget the negative sign here. So this would be the internal bending moment for the section between G and E. Therefore, the elastic curve for when we consider the right side would satisfy EI over second derivative of deflection equals to mx. And what is mx from here would be minus AP over A plus BX plus AP. Okay, and again, similar as before, we can integrate with x. We would get the local slope EI times slope of dy over dx would be minus AP over 2 times A plus B, x becomes x squared, and then the second term AP become APX, and don't forget the another integration constant, we call it C3. And if we integrate the slope equation one more time, we would get local deflection when we consider the part from G to E. And then the integrate again, we would have AP, AB in the denominator 2 now becomes 6, x squared become x cubed, APX become half of APX squared, C3 becomes C3x, and don't forget additional integration constant C4. And again, for this case, we have 4 boundary conditions. Left side, no displacement. Right side, no displacement or deflection. At the G point, or x equals A, the local deflection or vertical displacement has to match, and also theta, the local slope, has to match. Okay, so totally we have 4 unknowns from the integrations and 4 boundary conditions. Again, this is what we have. When x is to the left of G, we have the slope, we have the deflection. When x is between G and E, or between A and A plus B, we have additional slope equation and deflection equation. Consider the boundary condition. Now let's consider the boundary conditions. So we said at left end D, when x equals 0, the local deflection is 0. So x equals 0, this term is 0, this term is 0, we would have C2 is 0. We at least know one of the integration constant is 0. And then at the other end, at the E end, when x equals A plus B, the vertical deflection is also 0. So now, for this equation, when x equals A plus B, which means the first parameter keep, x cubed becomes A plus B cubed, and this half AP keep, and x squared become A plus B squared. And the third one, C3, we have x is A plus B plus C4 is 0. Now let's simplify this a little bit. So AP we keep, and AB and AB cube cancel is AB squared. So we would have AB squared, AP times AB squared, and this is 1/6 minus, but plus 1/2. The net would be 1/3 of AP times AB squared over 3. The second term, C3 times A plus B plus C4. Okay, and we would arrange A plus B times C3 plus C4 would be minus AP over 3 times A plus B squared. Now let's consider the additional boundary condition that deflection has to match where the load P is, or at x equals A, At the G point, the deflection from the left side analytical equation has to match the deflection from the right side analytical equation. So from previous, we would have EIY equals the left side would be BP over 6 times A plus B, A cubed plus C1A equals to the right side deflection minus AP6 times A plus B, A cubed plus half of PA cubed plus C3A plus C4. Okay, so the right side deflection has to match left side has to match right side deflection. And if we simplify C1, AC1 keep AC3 move to the left becomes minus AC3, and C4 move to the left is minus C4 equals the first term AP over 6A plus B A cube keep, this term keep, and this term move to the right side. We have a minus sign in front, and plus half of PA cube, and then we would simplify half PA cube we keep, and these two terms, when we add it up together, the denominator is the same. The numerator we put P commonly at the end, A cube commonly at the end, and then we have A plus B, and if we A plus B, we would cancel. The result would be minus 1 over 6 PA cube plus half of PA cube, and then you added them up together would be 1 over 3 PA cube. Okay. Consider the other boundary condition, that the slope of the elastic curve also has to match at G point, or where the load is. Then we have x equals a, the theta, the slope on the left side has to match theta, the slope on the right side. So for the dy over dx times ei term, the slope on the left side from previous is this guy, the slope on the right side is this guy. And again, we would C1 keep on the left, C3 move to the left side, have a negative sign, and minus AP2 over A plus B A squared. This term move to the right, has a negative sign in front, and APA becomes P times A squared. And for these two terms, A squared we keep at the end, the denominator is the same, 2 times A plus B, and the P we put at the end, then we have A plus B, and don't forget both have negative sign, so negative sign in the front, and A plus B cancel out. We would have minus half PA squared plus BA squared would be positive PA squared. From previous slide, we said at x equals a, or the G point, the slope on the left should match the slope on the right, and we got C1 minus C3 equals half of PA square. And for this one, if we times both sides by a, we would have a times C1 minus a times C3 would be half of PA cube. On the other hand, from the local deflection match at A point, we have A times C1 minus A times C3 minus C4 would be 1/3 of PA cube. So these two combined, we would have the first two terms would be half PA cube minus C4 equals 1 over 3 PA cube, which means C4 move to the right is half minus 1/3 of PA cube, or 1 over 6 PA cube. Okay, and finally recall that at the E end, at when x equals a plus b, the local deflection is also 0, which means for the a a plus b c3 plus c4 equals minus ap over 3a plus b square. And with these two equations, we would have a plus b c3 plus a 1 over 6 pa cubed equals this whole thing. So a plus b times c3 would be minus 1 over 6 pa cubed minus a p over 3a plus b squared. And of course, if we expand, if we move a plus b to the right side, we will have c3 minus equals minus 1 over 6 a plus b pa cubed minus a p over 3 a plus b, because square and ab term cancel. Okay, so we would have the C3 term, C4 term, and C2 term we know is 0. So finally, the C1 from here, C1 would be C3 plus half of PA square, and the C3 would be this whole thing, 1 minus 1 over 6 PA cubed minus AP plus A plus B plus half of PA square. And if we simplify a little bit, we would have C1 equals this is 1/3 of PAB and minus A square over 3P plus half PA square. That would be plus 1 over 6 PA square, and the first term we keep is 1 over 6 A plus B PA cube. Okay. For the deflection curve, for the left side of x from 0 to a will be the EI times y. The deflection would be the BP over 6 times a plus b EI x cubed plus C1x. And C1x we know is this long equation, so we can write them up together. We put EI in the front, so we would have BP over 6 times a plus b x cubed plus this C1 term, which is minus all this times x. And we can of course simplify this a little bit. This the first term we keep, the second term, this one become here, and the third term we times both a plus b, and 3 becomes 6, so we have 2 a plus b, the third one over 6 a plus b, and we put them together, EI in the front, 6ab, every term has 6ab, so 6ab also in the front, and p also p put in front, so we have bx cubed. This one would have minus a cubed, this one would have, we expand, would be minus 2a squared b, and then this one would be 2a b squared, don't forget minus sign, and then plus a square a plus a cube a square plus b, and then we have x for this term. And a minus a cube cancel, minus a square b plus a square b becomes minus a square b minus 2ab square x, and now we put b also in the front, we would have x cubed minus a square plus 2ab x. Okay, so this gives us the so-called analytical solution for the y deflection in this case. Therefore, the deflection curve on the left side of x from 0 to a would be given by this long equation. And when x equals a, right at the g point, the y deflection is just when you put x equals a there, bp 6ei times a plus b in the front, a cubed minus a squared plus 2ab times a would be a cubed minus a cubed minus 2a squared b, a cube cancel each other, and the minus sign in the front, 2a squared b squared p over 6ei, and a plus b, and 2 and 6 cancel 1 over 3. Okay, this gives us the local deflection where the concentrated load is applied, or at the G point. Homework 9.3. A prismatic cantilever beam on the right side E, it is clamped, it is fixed onto the wall with this DE beam, E side cantilever fixed on the wall, and the D side is on a roller. It is subjected to a local moment m0 applied at the D side or left side. We want you to step by step determine the elastic curve yx. Elastic curve yx. Y is for vertical deflection at location x, and also the reactions at D and at E. So like before, we would first draw the FBD or free body diagram for the entire beam. This DE beam, we have external local moment m0, and at D, let's assume there is a local reaction force RD, and at E side, let's also assume that's a reaction force RE. And because these two forces are vertical, they should balance each other. So if I draw RD up, and RE must be going down. And then let's assume that's also a internal, there is a reaction moment ME moment from the wall to the E side. Okay, let's by convention, let's draw it counterclockwise. So the balance of force would give RD in magnitude the same as RE, and they are opposite direction. The balance of moment around the E point, the balance of moment around E point would give M0 counterclockwise, ME counterclockwise would be balanced by RD times the distance L. Okay, so now how many variables do we have? We have RD, RE, ME, and ME is 3 variables and only 2 equations. 3 variable and 2 equations. So this is so-called a statically indeterminate problem, which means by pure statics consideration, these 2 equations we cannot solve for the 3 unknowns, RD, RE, and ME. So it doesn't mean it cannot be solved. We have to now consider deformation of geometry in order to solve for the problem. So let's consider an arbitrary section DG of length x from D. DG, let's draw the free body diagram. We would have DG, we will have same RD, direction force at RD, and at G, let's assume that's a internal vertical shear of V, okay? And let's also assume that's the internal bending moment mx, internal bending moment. From balance force point of view, RD and V should be the same in magnitude and opposite in direction. If RD is drawn to be up, the V has to be down. And let's also consider the balance of moment around the G. Balance of moment around G, we would have M0 trying to rotate it counterclockwise. We have internal bending moment M also trying to rotate it counterclockwise. And these two are counterbalanced by RD times this distance from D to G, which is x. As a result, internal bending moment mx would just be Rd minus R0, would just be Rd minus Rdx minus M0. So from previous internal bending moment, mx is Rdx minus M0 for arbitrary section from D to G. The elastic curve would satisfy EI times second derivative equals internal bending moment mx equals Rdx minus M0. And if we integrate with respect to x for one time, we would get the local slope EI times first derivative would be half of Rdx squared minus M0x plus C1. And M0 is the external applied moment at D. Rd is the reaction force at D, which we don't know. C1 is the integration constant. And if we integrate with respect to x again, we would have the local deflection y times EI would be 1 over 2, now become 1 over 6 Rd x2 become x cube minus M0x become minus half M0x squared, C1 becomes C1x plus C2. Okay, now we have an additional integration constant C2. So now we have totally 5 variables, which are Rd, Re, Me plus C1 and C2. So totally 5 variables, and we have from statics we have 2 equations: balance of force and balance of moment. But now we also have 3 boundary conditions. At the D side, we said the local vertical deflection would be 0, x equals 0, y equals 0. This point cannot go down. And at the E side, we said at x equals L, the local deflection y must be 0, and at that same location, the local angle, the local slope must be 0 because it's clamped. It cannot rotate freely from the original location. Okay, so we have 3 boundary conditions, 2 equations also from balance force and balance moment. So 5 equations, 5 unknown in principle can be solved. And in particular, at x equals 0, y equals 0, at D point, it means for this equation x equals 0, this term is 0, this term is equal, this term is equal 0, the C2 term is 0. Okay. Then at the other end, x equals L, or the E end, the deflection is 0, which means 1 over 6 RdL cube minus 1 over 2 M0 L square plus C1L equals 0. And at the same time, x equals L, theta is 0. X from the local slope is 0, which means half of Rdx square L square minus ML plus C1 equals 0. Okay. So from previous slide, we said C2 is 0. We still have 4 remaining variables: Rd reaction force at D, Re reaction force at E, Me reaction moment at E, and the first integrate constant C1, and 4 equations. We know from statics Rd equals Re, and M0 plus Me equals Rdl, and the third one is 1 over 6 R from previous slide, 1 over 6 Rd L cube minus half of M0L plus C1L equals 0. And lastly, half of RdL square minus M0L plus C1 equals 0. And from the last one, we would have, arrange times both sides by L, half of RdL cube minus M0L square plus C1L equals 0. When we combine these two together, we would have the C1L equals, so 1 over 6 Rd cube minus 1 half of M0 L square equals half of RD L cube minus M0 L square. So M0 from here we would have the 1/2 RDL cube minus 1/6 becomes 1/3 RDL square equals M0 L squared move to this side becomes half of M0 square, M0 L square, and as a result, the RD would be 3 M0 over 2L. Okay, L square, L cube cancel become L. I'll go to the other side. So now we get RD, and RE would be the same value. So as a result, RE would be the same in magnitude M3M0 over 2L. And for the third one, M0 plus ME equals RD, which means the reaction moment at E would be RDL minus M0, and the RD is 3M0 over 2L times L minus M0. LL cancel, and D is half of M0. Okay, and finally, half of RDL square minus M0L plus C1 equals 0. C1 would be M0L minus half of RDL square. MDL we keep half. RD is 3M0 over 2L times L square. It's 3 over 4 ML, and M0L minus 3 over 4 becomes a quarter of M0L. Okay, so this gives us the C1 value, RD value, RE value, reaction force at D, reaction force at E, reaction moment at E, and the last integration constant. Earlier we said the elastic curve satisfy EI y deflection is 1 over 6 RDX cube minus half of M0X square plus C1 X, and C1 is from previous page is M0L over 4, and RD is 3 M0 over 2L. So you plug them in, 1 over 6 RD becomes this one times X cube minus half of M0 X square plus C1 becomes M0L over 4X. And if we combine them a little bit, 3 and 3 cancel, 4L in the denominator, M0X cube minus half of M0X square plus M0L over 4X. And we can get Y would be EI divided by everything divided by EI M0 or 4EIL X cube minus half M0 X square EI plus M0L over 4EIX. Homework 9.4. For a cantilever beam with both distributed load W and concentrated load P, as illustrated, W is P equals to P over L. L is the total length for this cantilever beam. Okay, we want you to determine the slope and the deflection at the D end, the left end D. Okay, so it is two load. One is a concentrated load, one is a distributed load. The concentrated load is applied at the midpoint of the cantilever beam, while the distributed load is applied throughout the beam, uniformly distributed load. So the hint is to treat the concentrated load at G at the center alone, and then the section GE would behave like a typical cantilever beam with a vertical load at the end, while the section DG for that concentrated load would remain straight because that part has no applied force on it. Okay. So this combined state would be the superposition of two simple loading scenarios. One is just the cantilever beam with a uniformly distributed load on the left. The other one would just be a cantilever beam with a concentrated load applied at the center, and the rest is free. Okay, with that kind of like for the rest free, you can treat this section as a straight. And the overall deflection at point D would be the linear addition of the deflection caused by W distributed load plus the deflection YD caused by concentrated load P. While similarly, theta, the local slope at the D would be simple linear addition of the slope at D caused by W, the distributed load, plus the slope at D caused by the concentrated load P. So these two are our so-called superposition equations, and applied when each of the load and deformation are relatively small, well within elastic limit. Okay. First, for the distributed load W over prismatic cantilever beam from our appendix D, as we took out from the textbook, we borrowed it out from textbook. For case 2, you look at these are essentially exactly the same, except we flipped it from left to right. So the deflection at the D, it would be just simply the maximum deflection. And what is this distributed load? Here we call it W, but in this case, W equals, we know, P over L. Okay. So the maximum deflection, would be WL to the power of 4 over 8 EI. That's the original one. You have a minus sign because it's going down. It's deflecting downward. And the minus W, we are going to replace by P over L, and P over L times L to the power of 4 becomes PL to the power of 3. So this would be the deflection caused by distributed load alone at the D. Similarly, the slope at the end D, which is end of the cantilever, due to the distributed load from here, slope at end would just be WL cube over 6 EI. And here we have negative because in this plot it is going kind of downward trend from here. But in here, because our beam will bend like this, so we would have positive. So I have positive slope just to because the way we set it up, we said origin is on the left side. And what is W? It's P over L. So WL cube becomes P over L times L cube becomes PL square. And this thing is over 6 EI. That gives us the local slope at the D end due to uniformly distributed load throughout the beam. Okay. On the other hand, for the concentrated load P, remember, is applied at the center for the cantilever beam. It's still related to the appendix D and the case 1, except it is not at the end, it is at the center. So the deflection G due to the concentrated load P, deflection, it's at the far end would be minus PL cube over 3 EI, PL cube over 3 EI. But in here, because it is only at halfway, so the L essentially would be half of L in this case, and the negative sign because it's going downward. Okay, so it turns out to be 1 over half cube would be 1 over 8 times 3 would be 1 over 24. Don't forget negative sign. PL cube over EI, 24 EI. Okay. So that gives us the deflection at G point due to concentrated load. Similarly, slope at the G point, not at D point, at the G point due to concentrated load would be also related to here. Slope at the end would be PL square over 3EI, and it has negative sign here, but here because the way it deformed, it will be positive, and the way we define our equation, it will be positive P. And here, instead of using L, we are going to use this practical distance would be half L, so 1 over 2 square would be 1 over 4 times 2 would be 8 PL square over 8 EI. And again, the positive slope is due to the origin of the coordinate system is at the D point, at free end, and the axis is from D to E. So from previous slide, for the concentrated load, the deflection at the G point is given by this one. The slope at the G point is given by this one. And the total deflection at the D, because you are going to bend it here, but the DG section has no net force, so it's going to remain as straight or with infinite radius of curvature. Then the total deflection YD, the deflection at D point due to concentrated P, would be whatever the deflection at G plus, this is straight line side length, which is 0.5 L times sine theta, which when theta is very small, it's just the times this theta. Okay, theta G. What is theta? Theta is the local slope here, times theta P, and we plug the number in. YGP would be PL cubed over 24. Don't forget negative sign here, and we have negative sign here because it's going, everything is going towards below the horizontal axis. And what is theta? Theta G is PL square over 8EI times half of L, and this is negative sign because it's continue to go downward, and you plug the number in. PL cube and PL square, this is PL cube, PL square, L PL cube, put to the numerator, and the EI put to the denominator, 1 over 24, half of times 1 over 8 is 1 over 16, and when we add them together, it would be 1 over 48, 2 plus 1 over 16, 3 minus 5 over 48. Okay, so this gives us the total deflection at D point due to concentrated load applied at the center of this cantilever beam. And on the other hand, because the remaining section remains straight, so the local slope at the P end would just be the local slope at the G point, and it will just be PL square over 8EI. So the last step would be superposition of the two effects. The total deflection at D would be the deflection at D caused by distributed load W plus linear addition of the deflection at D caused by concentrated load. And from previously, the distributed load gave us PL cube over 8EI minus because it's going down, and the concentrated load caused deflection of minus 5 over 48, this PL cube over EI. And then when you add them up together, the total deflection would be minus, and you add that up, 48, and 8 times 6, 11 PL cube over 48 EI. The total slope or angle at the D point would also be the slope caused by distributed load plus the slope caused by concentrated load, and this is the the slope caused by distributed load would be PL square over 6EI, and the slope caused by concentrated load would be at the G point would be PL squared over 8 EI, and when you add these two up, it's also 24, and this has a factor of 3, this has a factor of 4, it's 7 PL squared over 24 EI. Okay, so now we know the total deflection as well as the total slope at the D end caused by the combined loading from distributed load and the concentrated load.